So 10 is a leaf node and 75 is like one level below it, and 300 has multiple levels below it.
75 has one child. 75 has only one child. And after you remove 10, it has only one child. And 300 has two children. That is the difference. Is that clear?
Yes, sir.
Now, suppose you have to delete 10. Is there something difficulty? Is there any difficulty in deleting 10?
No, so we can just remove it.
Just remove it and put the, suppose, yeah, so left pointer of 75, you put to null. That's all. Left pointer of this node will go to null. Okay. Now, if you delete after this, suppose you want to delete now 75. 75 has one child. So what would happen in that case? What you would have to do if there is only one child? What would you have to do?
So replace 75 with 90 and then just
That's all.
delete.
I replace 75 by 90. So I put elevate 90 to that position. What does that mean? So the left pointer of 700 would point to 90, right? And yeah, if you're not keeping parent pointers, nothing else has to be done. You just take this left pointer to 90. That should suffice. That should suffice. Okay. If you are keeping parent pointers, I discussed, you have to do some more things. And if you think about it, it's not difficult. Suppose you're giving parent pointer, the 90's parent is 75. Now you have to change that to 100. Okay, that was all. Anything else that we have to do?
No, sir.
Sure. So this was the second case. And what was the third case? I have to delete a node that has two children, right? And now I am in a fix. So how do I do that? Because in general, it can be a situation can be like this. I delete this node y, and there are two subtrees left and right. So if I have to delete it, this tree becomes disconnected. Tree becomes disconnected. So how can I delete this node? What do I need to do? And that is where we said, oh, why don't we use binary search tree property? What is the property? All the keys in the left tree are less than y, right? All the trees in the right hand tree are greater than y. Sure. Now I want to delete it with the minimum, with the minimum changes to my structure. What can I do? I can say, okay, let me find the maximum of the right hand side. Let me find the maximum of this right hand. Is that maximum or minimum? What do I have to find?
Minimum.
So
Minimum.
minimum.
So I find minimum of the right hand side. Okay. What do I know about it? It will be just the next number of after y. So all the numbers in the left will be smaller than that number, and all the numbers in the right will be larger than that number. Right? If I take that number out, and that has a term, we call that a term. What was that? Successor. Right? So if I find y successor, and it will be in the right subtree, right? Because the right subtree, I can just keep on going left, and I get that node. And right subtree exists. That's why I am in this case of a tree having two children. So I will keep on going down in the so finding the minimum here, and that node becomes a successor of y. And what I do now? What do I need to do now once I find the successor?
So we'll replace y by that.
Replace the key of this node by the key of this node. Okay? Only the key needs to be replaced. And then once you do that, after that you delete this node.
So why
Now,
are we using successor, not predecessor?
I said you can use predecessor, and somebody even gave a new different algorithm that was also fun.
Okay.
You can do the same thing
Okay,
with
sir.
predecessor. Same thing.
Okay, sir.
Is that
So
clear?
we replace the key and then delete the predecessor or the successor, whichever we choose.
Yes.
Okay, sir. Understood.
Now, okay. Uh, sure. Now, if you want, uh, I can quickly show the code for this. Will that help?
Yes.
Or
Yes, sir. It will be helpful.
let me see. If I can show any other questions on binary search tree? Meanwhile, hmm. Okay, I think let me just use your chat to show you the code. Hmm. Yes. Okay, so while I'm finding the code, this is where we were, right? And somebody asked me, what is this row? Anybody has an answer? What is this row? We said Fibonacci
Sir, golden
series,
ratio,
golden
Golden
ratio.
ratio.
What is golden ratio?
root 5 plus 1, root
Root
5
5 plus 1 by
minus plus 1 by 2.
Is that correct?
5 minus 1 by 2.
No, 1 plus root 5 by 2. It is correct.
One plus of five. What is the idea? What is your Fibonacci series? What is F0?
0,
0,
F1?
1,
1,
F2?
1,
1,
F3?
2,
2,
F4?
3,
F5? 5?
5,
F6?
8,
8.
Yeah, from F6 onwards, what do you see? So you can write F6 as F5 times golden ratio. So 1 plus root 5 by 2. And whatever you get, you take a floor. Yeah, I'm sorry, my laptop is creating some issue. I cannot directly do that. Let me put on chat. Let me see if that works. Hmm. Okay, and like that you can find out f7. So what will be this? This is 5 times. What is 1 plus root 5 by 2? 1 plus 2.8
1.6.
divided by 2, something like that.
1.61.
1.61. So and you take a floor, you get 8, and that is what exactly what is f6. And you use this formula, f7 will be f6 times 1 plus root 5 by 2 in a floor. So that will be 8 times 1.61 and 1.65, I think. Right?
Sir, I think we need to round it to the nearest integer. Taking floor will give us
Nearest
f7 equal to 12.
Yeah, yeah. So it will be nearest integers, sure. Not exactly floor. So that will be just round. Okay. Yeah. So 8.8 times 1.61, the nearest integer will come out to be 30. And like that, you can find any next number in the Fibonacci series. Okay. Right. So that was row. That was row. And then you can write a formula that yes, f of h plus 3 is nothing but rho to the power h plus 3 divided by root 5. And then from there you can easily derive what is number of nodes are less than equal to this. Number of nodes are less than equal to this. So if you say n is less than equal to 1 by root 5 rho h plus 3. Oh, sorry. These are the minimum number of nodes. So number of nodes will be greater than equal to this. N is greater than equal to this. Yeah. We found the minimum number of nodes in a tree of height h. So this should be this. And minus 1. And this will give you h is less than equal to log of n plus 1 plus log of root 5, right, divide by rho minus 3.
Sir, I think it will be log rho.
Log, log of. So then from there you find yes, h is actually order log. H is actually order log. From this you will get. And if actually compute, you will get roughly 1.44 log n. But yeah, order log n is what you derive directly from here. So this was just the proof that if you actually follow AVL property, you get high dash order log. And today I wanted to tell you how do you maintain that track. Now, okay, so what I shared on the chat was a simple structure for binary search tree, right? And I think we covered that. So you can define it like a BST node. And suppose you want to avoid.
We are taking the nearest integer at every stage. So can we multiply them and take the nearest integer at last?
Yeah. So that's what we.
So like we are doing f6 as f5 into 1 plus root 5 by 2 and its nearest integer.
Mm-hmm.
Then f7 is f6 into 1 plus root 5 by 2 and its
Mm-hmm.
nearest integer. So can we write f7 as f5 into 1 plus root 5 by 2 whole square?
Oh, I don't think that actually works. That actually gives you the correct number. I think that messes up. So you have to do it by every number. If anybody knows otherwise, let me know. But I don't think that works.
Yes, sir, that's what I'm on.
That does not work.
Okay, sir.
So okay. Now what I so on the chat, could you see the simple structure for BST node?
Yes, sir.
And suppose you can now put another thing like, okay, I want to avoid writing BST node star again and again. So you can again do another type that BST node star becomes BST. So that way you can just define your BSTs. Right? And that will be a pointer. That will be a pointer to a node, to a BST node. So suppose you want to use that, and then you want to write your delete function. Okay, I think I'll have to just copy. Anything else is not working. Okay, so what I pasted is a code for deleting in iterative manner. This iterative code. So I hope you can see that. I'm just reading it. So you have this BST delete. Okay, I think maybe I can use this to actually write it. So you have this BST, that is the return type when you have to delete. And then you are inputting your actual tree, that is the root of the tree, and the key value. Okay, so you want to write a code for deletion. So first thing is, yes, it is using some other nodes. So you can use BST node, or you can just say BST PUV. Either is fine, or you can say BST node star P star U star V. So either will work. Okay, and then you can have, okay, you start initializing your node U to T and P as null. We will see why do you need that. And now, see, you only know the key. You do not know where your key lies, So you have to first search that key in your binary search tree. So you are writing an iterative code for actually searching that key. So the code is while U is not equal to null. So you started with the root node and you are searching until you find it to be null. Okay, and then you will check key. If P is equal to U, that means this is the node you have to delete, not U. Well, that means, yeah, this is the node you have to delete. Okay. So you have to delete that node, then you have to find out, okay, which case it lies into. So in this, what is being done? The case 1 and case 2 are handled together. That is, if it doesn't have a child or it has only single child. So they are handled together. So because even we are saying, okay, what we are saying, if the left is empty, if U left is equal to null, or U right equal to null, that means it is one of the two cases, first two cases, not the case where both the children are there. Then accordingly make V as your new child. Accordingly make V as your new child. Okay. So you're calling. So yeah, this is just a syntax you would have seen. If U of left is equal to null, question mark, used to right, left. Okay. And if your P was null, that means your PHP. So this was the case when the root itself had to be deleted. So other case you have to take care, else if this value is less than this is less than the value.
Sir, what is the P equal to null? Can Hello, sir.
Yes.
Sir, here we started with P equal to null. Then why are we checking if P is null or not?
Right. Okay. Yeah, let me first get this entire code. See, what is P here? So P would be your parent by which you will start your next iteration. So P is like the parent. So you started with U is equal to T, that is the root node, and P is the parent. P is the parent of that node. That is null right now. Okay. So we are maintaining the node and its parent. So iteratively we will do. Next time we will update P to be that particular node from which we came. So this, yeah. So what we did here, this U is the node on which we will search. Node we are searching. P will store the parent of that, parent of U, and V we will use to create a new node. So what you see here, we started U as the T, the root node, and parent was null. And then we are searching for U while U is not equal to null. So we're searching for that and we're checking for our key. We are matching with the value of U. If it's left or right is null, you mean it is in first two cases. In that case, you check this condition and accordingly you will put VH either U of right or U of left. Okay. And there you are saying if the parent is null, then just make V as the, so V becomes the root node, T equals to V, T equals to V. So that is your node. Is that part clear? This particular code, is that clear? What is happening here? If the left child is null, you will put inside V what is the right child of U. Otherwise, the right child is null, you will put what is the left child of U. Okay? And even if it doesn't have any child, fine, that is null. So then this becomes null itself. And if the root was deleted, that means your root is null. Is that part clear?
Sir, if we are changing T, then shouldn't we call T by reference?
Right. In this case, we are simply saying that you return the root of the new tree. Then we can return this T. Okay. So we are
Okay,
returning the root of the tree. Depends what you're returning. So we'll return what is your new root of it. So
Sir, even then we shall call BST star T, because if we are not using return value as BST, then it is BST star star.
no, return value is BST, right? BST is already BST node star. BST is BST node star. That is a pointer already.
Yes.
This is BST node star. So we are returning a pointer to the root, and that is what is the input. So I define BST as base node star. So this is the part when this is not null. Okay. Sorry, when you found actually the value. But suppose you did not find the value, then what happens? So then you are either finding left or right. So then you have
Sir, like
yes.
when we are assigning T to be V, so aren't we destroying the whole binary tree? Like we are changing.
When we are assigning P is equal to V, then aren't we?
Like we are disturbing the whole binary tree. We are changing.
No, we are not. You see, we will do that only when we are deleting the root node. You see, we are deleting the root node. Only when we will do this.
Yes, sir.
So this is the very special case. You are deleting the root itself. This is like deleting root. So then you have to anyway do this. Change the pointer to change that pointer itself because your root has changed now. Only then. Otherwise, you will never assign something to T. But if root has to change, your root has to be deleted. This is what has to be done. Okay.
So then shouldn't we initialize T with T dot parent? I mean TR of parent instead
No,
of
the
null.
parent of root is null. Right? Parent of root is null. See, in general case, we will not do this. This is only happening if P is equal to null. If P is not null, then we will do this. And then there will be, yes. if P is not null, that means yes, we are in a case where we are deleting something other than the root. Parent is not null. Okay, so parent null only tells me this is the root. You do something special. So then you have else if. So I'm just starting from here. If P is equal to null, that means the node you are deleting, the parent of that is null. So then you simply say, okay, I have a new node as the root. That's the thing you are doing. But this is the very special case. Else if so now you will see the value of key. Okay, so if key is less than, so what does that mean? So this will happen if P is not null, you don't have to do anything. Already V has been assigned. V has been assigned to either you dot right or you left, one of this. But only if P is null, you have to put P as V. Otherwise, you don't even have to do this part. Okay. In other cases, you don't have to do this part. Now then you are going to else if. This else if corresponds to this if. If key is equal to u dot well, else if. Else if key is less than u well, then you know you have to go into the left hand side. Okay, so then
So where
say,
did the
okay,
inner if end? There was an
right,
inner
that's how,
if closing braces of that.
okay, okay. What did I do here? Mm, what did I do here? Huh. Okay, good one. So here, huh. Thanks. So what happened? If P was null, I did this. Otherwise, P is not null. That means I have to also change the either the left or the right of P. Yes. So actually, I'm writing that. So I'm not doing this for this if. I'm actually doing it for this if. So if P is null, yes. And for this if, right, yeah, for this if, else if P is less than u dot u well, you have a u that you are deleting, and you have a key that doesn't make,
Sir,
it
I
should
think
be,
you did P arrow well.
yeah, I missed that. I missed that. Yes. There should be this P arrow well. Yes, P arrow well. Then it will be this way. So now I'm checking this new node, is it coming to the left of the, is it the left of parent or right of parent? If key is less than the value of the parent, it will go to the left of this. So that means you have to do P left is equal to this new node V. And here you can say else, okay, else you can say P right equal to V. Okay.
Sir, I still have doubt in this
See
P.
what I did not do?
Sir, here, shouldn't we change the P again and again?
No, you will do that. You will do that.
Sir, can you scroll up a bit?
Yes.
Sir, here we initialized P with null, and when we come down,
Yeah,
here
we will
we
change P. We will change P. Don't worry. We will change P. What will happen? So now, after this, this loop has ended. This loop has ended. Okay. So this loop has done. Okay. Now, you check if the value is, if you found the value or not. Okay. If it is same, if the node has that, node has the key. Okay, that part is done. If node is same as key, if else if, and this if is also done here. Yeah, this if is done here. If t equal to u dot well, and that would not be the general case, right? So else, then you go else. Else means now you will go down. You will go down. So that point of time when you're going down, now you will change your parent. So parent will go to your previous root node, previous node u, okay? And where will you go? And where will you go should, so okay, what was my V? V was the new node that we had. So
So the while loop will keep running until we find the key, right?
yes.
So sir, after this, like to make it simpler, we could use like the successor function, predecessor function,
Yeah,
like instead of writing all.
no, actually we are doing that. I'm having a little hard time because I have not taken care of the parenthesis very well, the indentation very well. Okay, so I'm mixing up all, mixing up all. So just give me a second. So what is happening here? What actually should happen? So what should happen if your key is same as you well? Okay, you can still have all the three cases. You will actually have all the three cases. In this if loop, you tried the first two cases, right? And accordingly, you are defining this. You are defining this. But then you would have the third case uh, that will be the else of this, else of this. If both, I mean, none of them is null, that means I have the case with two children. Key is equal to u dot well, but I have both the children. And that is the case where you have to find the predecessor or successor, predecessor or successor. And that is this else. That is what this else should be. This else should be for. This if is for this and else is for that. Else means I have to find the predecessor or successor. And replace. I mean, you replace the key. And that is what I have to do. And that is what I will now do. Okay, else. So I have to find it. So what I am doing here, I am finding the largest element in the left subtree of U. Okay, what does that mean? I am finding the predecessor. I am finding the predecessor. So I am finding the predecessor actually. Largest element in the left of U. Okay. So I am at U, and I have to find the largest in the left. So that is where I'm at U. So I'm saying, okay, my P becomes U, and my V becomes U left. So this becomes my P, and this becomes my V. Okay. Then I keep on doing that until I find that V does not have a right. Yeah, to go to the rightmost of V. So while V right is not equal to null. Okay. Then what I do, I say, okay, let's keep on using P and V. So P becomes V, and V becomes V dot right. Yes. Okay, makes sense. So this will give me at the end what is that actual largest value. So once I find that V, so V will be the rightmost element here, V node, then I can replace the value of U with the value of V. So I can say, okay, U well equals to V well. That is just replacing the key. Okay, and now once I do that, you see, remember what was in the other part in this case? The other part was I had to delete this V. I have to delete V. So now delete V is being done. Okay, this is I have copied the value, and delete V is simply being seen over the simplest case. Okay, if P is equal to U, P left is V left, because P is the parent of V. Okay. Yes. Else P right equals to V left. Oh. Right. So if I found it in the sure. So what is this logic? This logic is simple, that you have this P, and now you will keep on moving your P here, here, and here, right? So if P was actually U, you will make you are deleting V. So V is here, you are deleting V from here. Okay, but otherwise this is in the right side. So if P is equal to U, P left will become V left directly. Otherwise, P right will become V left. V only has left, V does not have right. Okay? So V doesn't have the right side. Okay, let me wait. Is that making sense? No, I know I'm coding here like I'm coding for the first time, but still, is it making sense?
Sir,
Yes.
sir, if P equals to U, so we are assigning P left or U left as the left of V. So where would the value of V will be, sir? Means we have deleted V by
V
just
is something you have to delete. Yeah, right. V is the node you have to delete. You have to delete V. What is V? Remember, we had this U. We kept on going in the right subtree until we find the last element, that is the predecessor of U. Okay, so we find V. So V, and we said, okay, U well will become V well, and I have to delete V now. I have to delete V now, and that is where I'm checking. Okay, will V become the left child of P? Oh, sorry. So I have to delete V. So V does not have a right child.
yes,
Yes,
sir. V does not have a right child.
V may have a left child or it may be null.
Yes.
So what I'm
Yes.
doing, okay, parent, now this one I have directly assigned to the parent. Now this can be even
Hello, sir.
Sir, you are not audible.
if we were it will be, yes. Yes, tell me. I'm listening.
Sir,
Sir,
we
you are
have
not
to.
audible.
Yes. Oh, somebody said I'm not audible. Am I audible?
Yes, sir, you
Yes,
are
sir. Now you're.
audible. While you were explaining, you got cut in the middle.
Okay. Now tell me, what is the doubt? What is the doubt here?
We have to remove U because sir, we checked using the if condition that key is equal to U of well.
See,
So
that
we
is what
have to.
remember, that is why the theory is important, right? In theory, what we said, if it is one of the two cases, we handle separately. This is the third case. This is the third case. The third case
Yes,
we are
sir.
doing. Right? In third case, we don't remove U. What we do, we find that V as the predecessor, we were found this V as the predecessor of U, and I change the value of U as value of V. So this is what I have done here. Now I have to delete P. I have to delete P.
Yes, sir. Yes, sir. Yes, sir. Yes, sir. Got
Now
it,
you
sir.
can do many logics. Here is one logic is implemented. That is okay. You keep on seeing where is your P. If P is here, that means the left of V will come to the left of P. Otherwise, P is here, so the left of V will come to the right of P. That is the logic that is implemented here. And you can do with other logics also. Okay, and then yeah, your else is done, and then you can say, okay, I will return my T. I return my T. Okay, and then you complete your, so that means you are done. You have, see, once you have done this part, either case 1, case 2, you are done. You can simply say I will return T, whatever your T is right now, and you end this. Now what have you ended actually? You ended the part when key was equal to U well. Yes, you ended key equal to U well. But there are other cases where P can be less than UL or larger than UL. So that you have to take care now. So then you will say, okay, so this is done. Now you change your P to U, parent becomes U, and where will you go depend on what is your key. If key is less than UL, okay, what will be U? If key is less than UL, what will be U?
You are left.
I have to go left. Yes. Or else I have to go right. And this will simply just continue the while loop. Okay. When you did not find the key, this will continue. And at the end, you return. This is what happens in an iterative code. Now, just tell me, I know I did not do it very nicely, but still, does that help you? I mean, does that help you clarify, or did you find it completely like boring? I should have prepared a bit more for explaining. Or yeah, just give me some feedback. I mean, did you find it useful, not useful, or should have been done differently?
Sir, I have understood most of the things, and the rest I will do of my own in
Sure.
practice.
Okay, yeah, sure. Yeah, next time I'll show you code. I'll be prepared better that I can. Okay. This was a very long code, and that is why this took some time. But yeah, I hope you at least something's worked clear. Now, okay, tell me what else is bugging you in BST? What else is bugging
Sir,
you?
can you please again tell about that row-wise traversal of BST? Like, how do I get the elements of in row-wise?
So you are saying, different traversal. This is a root node, and suppose like that. So you are asking me, how do I get this, then this, and this, like
Yes,
that?
sir. Yes, I was having problem while trying to implement it myself.
Okay. I think you will have to use some sort of, I mean, the idea would be either to use some sort of stacks or queues. That is what I think.
So we have to use queue.
Right? You have to use queue. See, and this idea will be very similar to what the TA told you on how to take input, right? This you have to use this very similar idea here.
So like I was trying I was trying to implement it using Q. Like when I get a node, I was pushing that its child edges. But won't the graph then proceed like farther to the extreme left gradually instead of like checking the right wall also simultaneously? Like if after I implement the second row, so it will just directly go to the third row of the
Let's
left
see
and
what
the
will
fourth
happen
of the
to
left.
suppose this is 1, 2, 3. Don't worry about the actual integer numbers. I'm just giving an index 4, 5, 6, 7, 8, 9, 10. Right? What will happen? You first one, and you will put 2 and 3 in your queue. Right? So you see 2 will happen before 3, and only when you DQ you print. When you DQ you print. So for 2 you will put 4 here. Yes. And for you DQ and print.
Achha, while taking okay, sir.
Okay. Anything else? You see, things are not difficult. Yeah. I understand. You have to practice, and even you see, I will. If you tell me, if you ask me questions, I will not be able to answer most of this. But yeah, I mean, I can practice and answer. Maybe something. You will be in a better position to answer than me. I mean, if you ask any arbitrary question, because you are practicing, I am not really. Yes, but yeah, I will try. We will try to help you more by giving you some standard practice questions. We will do. Anything else you are like finding difficult in PST right now?
So finding successor, can you explain?
Successor, let's find successor. Yes, tell me what is the problem. Let me go to theory is clear. Is the theory part clear?
Yes, sir.
I also wrote a pseudocode, right? I also wrote a pseudocode.
I have doubt when there is no leftmost child in right field.
Yes, this was the thing. Right? No, was that the thing? No, this was inside. Yeah, this was the thing. Successor.
Yes, sir.
Okay. Now tell me, what is your actual doubt? We were finding successor of 2. We find successor of 2. So what we said, this is just a pseudocode, not a C code. I'm more comfortable here. But yeah, we can write a C code if you want. We can try together. Right? We will help to help. Okay. So successor of x. So what we did, yes, if right of x is not nil, this is easy. This you said is easy, right?
Yes, sir.
Otherwise, this is already written. So you have to say yh parent of x. Parent of x. So you have to say what is parent of x? 1. Okay. So y is parent of x. And now you say, okay, I keep on finding, I will keep on going up and up and up until either I reach the root, I mean top of root, or, so I have 2 things. So let me write it very clearly. I have 2 things. I have x, I have y. I'll use x and y, and I'll keep on moving up. So next iteration, what will happen? So this will become x, and this will become y. And like that, I will go. Okay. So when will I stop? Either when y comes here at null, right, and x comes here, or if a condition comes when, because what do I know here? X is the this node that I have to find successor of. I have to find successor of this node x. So let that value be some z. Then I know x is the predecessor of z. X is predecessor of z. I know that. That means x will be the rightmost element in the left subtree of z. Okay. Yes, I know that. So I have to find that z. I have to find that z using x. So what I'm doing, okay, I'm saying, okay, I will keep on going up as long as this remains, this x remains, as long as this x remains the right child, I'm fine. That means I am in that subtree. If x remains the right child of its parent, I'm in that subtree. But as soon as the x becomes the left child, what can I say? You tell me. As soon as the X becomes the left child for the first time, what happens then? If it was right child, I'm fine. As soon as X becomes the left child of its parent, what does that mean?
The value becomes smaller, sir.
Yes. And have I found the actual successor? What will be successor? Isn't Y the successor?
Yes.
So what is happening? I have Y or whatever Z, call it Z, and then I have its left subtree, and that is where I have X. X is the predecessor of Z, and Z is the successor of X. I have to find it. So that means I keep on going up, up, up. If X is the right child of the parent, I have no issue. But as soon as X becomes the left child of the parent, that means that parent is my actual successor. And that is what you see in the code, in the pseudocode. While Y is not null and X is the right child of Y, I keep on doing this. What do? I go up. So how do I go up? Y is parent of X, so I say, okay, X is equal to Y, and Y is equal to parent of X. X equal to Y is equal to parent of X. That's what I do in this loop. Okay. And at the end, what will I return? At the end, when do I stop? Okay, that means I stop here. X is the left child of Y. So this will become, in my iteration, this will become Y and this will become X. And H will become the left child of Y. That means I will go out of this loop. I'll go out of this loop. If I go out of this loop, X becomes the left child of Y, right? Then what can I say?
Y is the successor.
Y is the answer. Y is the answer. You return Y. You return Y. Okay. Now, what about the case when there was no successor? What will happen if there was no successor?
So then we wouldn't have find any such Y because X would have been
No,
the
but then
right
you would
most.
have gone up. You would have gone up to the point, to the top of root. Your Y will be here, and this will be your X. Then also you can return Y null. There is no successor. You can go up to here. Then also you return Y, that is fine. There is no successor, that is null. You will return a null pointer. Okay, I want to hear from person who had this question. I didn't note the name. Who had this
Yes,
question?
it is fine.
Yeah. Now tell me, is that clear? Anything you want me to tell here? Okay. So anything else that is bugging you in this binary size tree? No, yes. Sure. So do you think I can do the AVL trees now? Should I complete the AVL trees now? Or what would you prefer?
Yes, sir.
Yes, sir.
I can do that now? Okay, sure.
So on this AVL is there for tomorrow's lab.
As I said, AVL tree will not be there tomorrow. Only BSTs will be there tomorrow. Okay? But tomorrow, Professor Anvesh will start dynamic programming. So I can do this AVL tree today. Is that okay? Sure. So okay. So Yeah, we had proved HH order log n. That's where we were. Now I have to tell how do you actually do insert and delete. I'll not do both. I'll just give you an idea about the insert. Okay. So sure. So I'm coming back in just 2 minutes. And then I'll start this. Okay, back. So I'm talking about insertion or deletion in insertion. Let's say insertion in AVL trees. So you see what will be the idea? Idea will be yes, you do it like you are doing for BST. Okay. So proceed like you do in BST. But what will be the catch? What is the catch? Where do you have to change? So while you are doing that, it may happen that your tree comes out of balance. So it may throw the tree out of balance. So in that case, when the tree is thrown out of balance, you have to do something additional. So some additional steps are required to maintain the ideal property. And now we have to see what are those. So let's see some examples of insertion. And let me actually give you a tree. So this is my tree. So while I'm drawing, please verify that I am putting the balance factors correctly. Okay, do you think the balance factors are fine? Leaf nodes will have a balance factor of 0, right? All the leaf nodes are 0.
73 is not balanced, I think.
73 is not correct. Yeah, it's not balanced, but I mean, whatever I put is correct, right? So its right subtree has a height of 1 and left subtree has a height of 0, right? So the balance factor will be right, HR minus HL.
Yes, yes, okay, okay.
Uh, here, yes, this is height. This height is 1 and this height is 2. This should be plus 1 and so on. So this is the currently the true. Now suppose I want to insert something. Let's say insert 71. Where will you go? 71, right, left, right. I'll put 71 here. So you see what will happen if I put 71 here? What will I have to do? So I will create this new node. Yes. Additionally, what I have to do?
Update balance factors of
I
all
have to
the.
go up. I have to go up and see, okay, because this new node has been added, this might have changed the balance of the previous nodes. So I'll have to see, okay, for its parent, the balance has gone from 1 to, sorry, it was 0 now. What will be the balance of the parent?
1.
Plus 1. Yes. Okay. So that means I go up. So I go up and parent's balance goes from 0 to plus 1. Yes, that is easy. I'll see the balance of the parent. If it is 0, I have added a new child in the right child. I'll change the balance to 1. Now, do I need to go further up?
Yes, sir.
Hmm?
Yes, sir.
Because if the balance has changed from 0 to plus 1, that means it has gained height. I'm doing insertion, I'm not doing deletion. So in insertion, 0 to plus 1 can happen only when I gain height. I gain height, so I have to go up. I have to go up. I have to go up, and its parent. Now, what is the balance? This has gained height. This is 1. This is the left is 1. Right is 1. So this balance becomes
0.
0. 0. Okay. Now, do I have to go up? What is the meaning of plus 1 to 0 in insertion? What would happen? Plus 1 to 0 means what? Have I gained height at that?
No change in height.
No.
No. So plus 1 to 0 means I'm doing insertion, something has gained height. Plus 1 means earlier my right subtree was longer than left subtree. Now the left subtree has gained height. Okay, that means the left subtree gained height, but overall height remains the same. At that node, I mean at the subtree rooted at the node, remains same, does not change. So this becomes very crucial. If I'm going from 0 to plus 1, that means I have to keep on going up. If I'm going from plus 1 to 0, I can stop. Okay. And of course, if there is no change, I can stop. If there is no change at all, I can stop. There's nothing has changed. So this is very important. Okay. So I stop here. Fine, good. Now let me insert something called.
So 72.
Yes.
Where will you insert 72?
72. Yes, let's insert 72. Or you want to directly do 72? Fine. Let's do 72. I'm with you. 72. Right, left, right, right. This is the place I have to insert 72. Yes. So
Yes.
Let me put another node. 72. All right. Now I have put 72. Now I have to go up. I have to go up and check for the balance factor. So I go to 71. What happens at 71? Its balance factor becomes
+1.
+1. Okay, let me use black for it. So this becomes +1. So it has gone from 0 to +1. That means the subtree has gained height. I have to continue going. Okay. So I have to continue. 0 to +1. So I continue. Fine, I go up. I reach 67. Its right subtree has gained height. This was the right child. It has balance factor has changed to 0 to +1. Right subtree has gained height. So what will happen to the balance factor of 67?
+2.
+2. Oh, it was already +1. It was already +1. Now it has gained further height. What will the balance factor? What is the height of the right subtree?
2.
1. What is the height of the left subtree?
-1.
-1. That's what we discussed last week. 67. Its left subtree is -1, right is +1. So that means the balance factor becomes +2. Oh, so then this becomes here +2. I'm in trouble. I cannot allow a balance factor of +2 in ABL3. Can't be allowed. So that means I cannot do anything else until I do something to resolve this issue. Yes, I have to do something to resolve this issue. So I think about it. What can I do to resolve this issue? Okay. So now let's try to see what we can do.
Sir, can we replace 67 by 71 and then left child of 71 will be 67?
Can we
replace 67 by 71 and then left child of 71 will be 67 to maintain height?
Oh, okay. Yeah, you're thinking good. But let's study formally. Okay. So what would happen? So we are in a case where at a node I am finding a balance factor of +2 or -2. Yes, +2 or -2. So I'm just telling you for +-2, but I will generalize that for +2. Okay. So I'll come back to this further in a while. So what happened now? So while going up, let's say we encounter a balance factor of -2. 20 + 2 -2 doesn't matter. Just for explanation, that's -2 is it. Now, when can that happen? That means it has gone from -1 to -2. Earlier, you can only increase by 1, right? It can only go from -1 to -2. That means its left subtree would have gained height during insertion. So that means what can you say about the balance factor of the left subtree? What would that be? So what will be the balance factor of left subtree?
-1.
-1. Can it also be +1? Why not?
Yes, sir.
Yes, sir.
So it would have become from 0 to -1 +1. Then only the left subtree would have gained height. Yes. And then you go up, it was already -1, it became -2 now. So that is the situation that we are in. Now we will see these two situations differently. One is when the same sign, so this is the same sign, -1, -2, and this is different sign or opposite signs. Now why they are different, let's see. let's take the situation same sign. Remember, we also had a same sign situation. This is +2 and +1, same sign situation. So let's see the same sign situation. What would happen? So let me draw this. So before insertion, what would happen before insertion? So I have this node U, balance factor is -1, and that has is left subtree. Sorry, same sign means it was 0 only, before insertion was 0. That is V, and let's say, yeah, that means it's both LL, LR, LL, LR. They have both same height, H. Okay, and the balance factor is -1. That means the overall left subtree is higher. So what is the height of the right subtree? R.
H.
Left subtree is H+1 right now. This is the case. Now you insert it. So after insertion, you want the same sign. So that means the LL has gained height. So LL has gained height. So what will this look like? This will look like this. U becomes -2. This becomes -1. V and LL becomes H+1. And LR becomes H. Okay, and right remains at H. So overall height of the left subtree is H+2, and this is H. Balance factor is -2. Now I have to do something to restore the balance. So what can I do? What can I do here? So as one of you was saying, let's do something like change UV with each other. And this has a very specific term. So suppose, think of it as a tree, right? And as if I am rotating it. Think about rotating it. So I rotate it and rotate it towards the right. Because right subtree is smaller, I want to give something to right subtree. And yeah, I'll tell what does that mean. But ideally, what I want to do, I want to rotate this. Right rotate. Right rotate with U. What does that mean? What will this do? Right rotation. So what would it do? It will bring V to the root of this subtree that I'm seeing, and U will become its right child. Okay, but where will other things go? Where will other things go? Let's see what happens in this rotation. Okay, so let me first define. Yeah, I'll just give you what will be the final answer by this. So you will have V here. So you will have V, and U becomes the right child, and R remains the right child of U. Okay, and U's left child remains LL. Sorry, U's left child becomes LR. And V's left child remains LL. Now let's do the balance factors. LL and R have the same height. Both are H. So U is balanced. Okay. LL had a height of H+1. And this has a height of H+1 also. So V is perfectly balanced. This is perfectly balanced, and this is perfectly balanced. That means I don't have to go up further. I'm done. After this rotation, I'm done. Overall tree has not gained height, you can see. Before insertion, what was the height? It was H+1. Now also it is. At this point, this was H+1. Q equals h plus 2. H plus 2. Now also the h plus 1 plus 1 h plus 2. Okay. So height has not changed at this same before insertion. That means I don't have to go up after this rotation. Are you convinced by that? I'll tell what happens in rotation. But suppose I achieve this, I don't have to go up. After a single right rotation. Convinced, not convinced, let's say something. H plus 1 height, h plus 2, h plus 2 height. And here also it's h plus 2 height. Height has not changed, I don't have to go. I'm done. Now the question is what actually I did? What actually I did in this right rotation? So in the right rotation, in general, what am I doing? So let me write it general form. So suppose I have a tree rooted at y and it has a left x. This has some subtree alpha beta and y has this gamma. Okay, so I can do a right rotation. Right rotate with y and I get x here, y comes at its left side, gamma remains as y comes as x's right child, gamma remains as its right child, x retains alpha and y gets beta. Okay. Am I allowed to do that? I'm doing something on binary search tree. Does that even follow binary search tree property?
Yes, sir.
Yes, binary search tree property, right? Let's write the in order traversal of this. So this will be alpha dot p will be less than x, which is less than beta dot p, which is less than y, which is less than gamma dot p. Or whatever, I mean, dot p can you can put on with x also. Sure. So forget about these alpha, x, beta, y, gamma. Now let's write the same for this. Alpha less than x less than, what should I write first? Y or beta?
Beta.
Beta, y, gamma. And you match them. Alpha, x, beta, y, gamma. Same thing. So they follow the same traversal. They are the same. So the BST property, binary search tree property, does not change. To rotation. Okay. And analogously, I can define a left rotation. Left rotate with x. And this is what I'll get. How much time this rotation will take? What am I doing actually when I'm doing this rotation? Suppose I have to do this, right rotate y. What will I have to do? Just let me write a pseudocode.
So left of y equal to beta and right of x equal to y.
But you don't have beta, you are only given y. You only given y. So first you have to get what is x. So x gives me y left. Right? X is y left. And beta is x right. Yes. Now you can say, okay, I have already got y is left, so I can say y left becomes beta. So then you say y left becomes beta. Y's right does not change. And x's right becomes y. And x right becomes y. Right? And then you can return x. As per appropriate function, you can return x.
Sir,
Yes.
sir, the parent of y is still pointing to y only, no, sir?
Okay, sure. Yeah. So here I was doing without parent pointers, but if you have parent pointers, you have to change that also. You have to change parent of y, change parent of actually many things. Parent of
Yes, sir. With 3 parent pointers.
yeah.
Beta
There's
equal to y.
some parent pointers would have to change if you are maintaining them.
And sir, even if we don't have parent pointers, still parent of y will have a child pointer. That
If
will
you
have
see
to
the
change.
parent pointers, then there's nothing called parent of y. You will compute it. Okay? There's nothing like parent of y directly. You will compute using the tree. If you are given it. So see overall what is there? This is just some constant things, some order one operation for rotation. Right? Just some order one operation you are doing, and that's all. That's all. And then you can maintain the property again. You can maintain the property very well in one rotation. So what happens? You went up, seeing the balance factor. As soon as it becomes -2 or +2, I did a single rotation, and it is maintained. I don't have to go. Okay. Now quickly, let me tell you what is the other case when you will insert in the right uh, subtree of V. So before insertion is this. After insertion, what will happen? Okay, let me just put it here. So this is what will happen after insertion. This will become h plus 1, and this will become plus, and this will become -2. Now what will you do? Now what will you do?
Change R
Sir,
with LR.
Hmm?
Exchange R and LR.
Can you do that?
sir,
No,
LL
no,
can
no,
become
sir.
the left child of U.
What can become the left child of U? LL. So you're doing a right rotation again. If you do a right rotation, what will happen? You see, this will be even worse. This will become even worse, right? Right rotation, you move that and you see this will become even worse. And if you do left rotation, same thing will happen on the other side. But left rotation is slightly better. Yes, left is slightly better. Left actually gives you an idea. If you do left, you can do something more.
एक मिनट रुक जाओ.
You can go back to the original, your earlier situation. You can do another right rotation, right? If you do a left, you will go to h plus 1 and h, and then you're back to your earlier condition. This is same sign as this, and then you do another right rotation. So actually, in this case, you have to do 2 rotations. So that means I have to also see this node more clearly. So let's write it here. So what will happen after insertion? So you have this U, and you have this V, you have this LL, and you have this you are breaking into another node W first, and because this left has gained height, so this is h minus 1, this is h, this is h. Okay, so this remains -1. Here the right subtree has gained height, so this will be +1, and this becomes -2. So h +2, and the right is just h. Yeah, this is the situation. Now what I have to do? I have to first do a left rotation here. Yes, left rotation. If I do a left rotation, what will I get? W will come here. Let's do this. So U, W, V, LL, and we have this. So LRL, LRR. We also get this LRL, and W returns its LRR, and this gets this. This returns this R. Okay, so that's what we have got by a single rotation, left rotation. Did I do any mistake here? H -1, H and H. Oh, still, but I'm not done. I'm not done because there's a balance factor of -2 even here now. Yes. Now what I have to do? I have to again do a right rotation. Now I do the right rotation. Okay. So after doing right rotation,
Sir, we will get back to the original configuration if we do right and then again left at the same position.
oh, I'm sorry. I'm sorry. Thank you. I cannot do right here. I'll go back there. They are like inverse of each other. What I have to do? I have to actually do a right here. Yeah. I have to actually do a right rotation here. So if I do a right rotation here.
Sir, here the balance at W became -2.
Doesn't matter. This is just an intermediate thing. Let's do this and then we will see again. So if I do a right rotation there, then W comes at top, U is the right child, then the R, and U gets LRR, and W gets V, and V retains its LL and LRL. Let's just quickly do the checks. So V has a balance factor of 0, both are H. Okay, U, this was H -1 and this was H. So U has a balance factor of +1. U has a +1. And what about W? So this height is H +1. Oh, are we getting W has a balance factor of 0?
Yes, sir.
Yes, sir.
This gets a balance factor of 0. And overall height remains H +2 here. That was same as earlier. So height does not change. Height does not change at the root node of the subtree. So I don't have to go up. Oh, that's a relief. So that means I can get two situations. -2 balance factor and its child has -1. Then I can do in one rotation. Another situation is -2 and child has +1. Opposite signs, I can do in two rotations. In both cases, you are done here. No need to go up. So you can maintain the balance factor just by constant number of operations other than your insert, right? So what is the overall complexity of insert then? What is the overall complexity of insert in AVL tree?
Order of login.
Login.
Login, right? And that is the trick. So you can use these tricks of rotation. Rotation is the only trick that we have seen. You can use rotation that maintains binary search tree property, and you can see what I have to do in this case: one rotation, right rotation here, one left and right at another node, right? Thanks for telling me. If you do left and right, you will get the same configuration, right? So by one rotation, two rotations, you could maintain your AVL property, and your insert is done. Now delete is more complicated. We will not cover that. In delete, what we will see, if you do delete, this will need order login, at most order login rotations in the worst case. But even if you need order login rotations in the worst case, what does that mean? What is the complexity of deletion?
The total order is also log n.
Order login. So while doing insertion or deletion in AVL trees, just by using rotations, you can maintain the property. Once you maintain the property, everything is order login. So if somebody gives you a question on balanced binary search trees, okay, they will use the concept of rotations, either in AVL trees or in red black trees. We are not covered red black trees. So we use rotations to ensure that this property is maintained, and all the operations search, insert, delete, they remain order log. They remain order log. And that is your balanced binary search tree. You can now, once any question says balanced binary search tree, you can assume all operations, search, insert, delete, they happen in order log. Okay. Now tell me, was the concept of AVL tree and rotation clear?
Yes, sir.
You can go back to your original tree and try the one that we started with. Try here. You will actually do this. You have +2 +1. You will do a left rotation here. You will do a left rotation here, and your 71 will come here. 67 will go here. 72 here, and then balance factor is +1. Overall does not gain height, and you don't have to go. And that's where this way. Okay, so yeah. I could have told a few more things, but it's already time. I think I took 2 hours, but the first hour was just on BSTs, and I hope you won't mind that. And this is all I covered for AVL. Now, okay, so this topic is done. I'll send you some problems, and as discussed, I'll try to give you some practice problems that you can solve, possibly on one of the coding platforms, right? We have a lab tomorrow. I don't see many people here, but still I will tell one thing. For your assignments, lab assignments, please do not plagiarize either from internet or from your friends. Okay, this is for you to practice. So if you plagiarize, we have to take a hard stance. In the first assignment, there were cases of plagiarism, and because it's the first time, we will only give a 50% penalty, but we will have to give a penalty. Second assignment onwards, if we find a plagiarism case, we will give a 100% penalty. That means you will not get any mark if the code is plagiarized. Okay. So it's very easy to see, okay, this problem has a similar problem on internet. Let me just copy that. But you see, once this problem has a similar thing on internet, many other people will find it, and code will be caught. Your codes will be caught, and you cannot say, "Oh, I copied. I did not give my code to someone else. I did not take that from anyone else." But if you have copied, you will find similarity. I can give you an example. So in class test, we have this question 4, right? And I did not check that has a code on the internet. That has a code on the internet. And I think many of you found that and just copied that as it is. Now, there was one change from that question. The change was that division by floating point was not allowed, but division by integer was allowed. But for divide and conquer, when you have to do m is equal to n by 2, people were using loops for doing that. Who uses loops for divide by 2? That was allowed. And that was like weird. Why would you use a loop for doing m is equal to n by 2? Just because it was there in the solution on the internet. So yeah, so telling it again, so please do not copy either in your lab or in theory. We will try to ensure that we don't give you a chance to copy, right? But sometimes you may find that question and you attempt to copy. Don't do that. It will not help you. It will not help you. So yeah. So that is all. So we will then meet tomorrow.
Sir, I have a question.
Yes.
Sir, I have a question regarding plagiarism.
Yes.
Sir, in assignment 2 or 3, there was this. I don't know. Actually, remember. We have to find the. We have to check if it is prime or not. Okay, sir.
Mm-hmm.
Sir, then I have used a SIFE function, which is like a basic, which is a very general algorithm, which can be found in various sites, and I have used that function.
When you see plagiarism, it means lot of code is plagiarized. So something like 50-60% of your code is taken from somewhere. If you're taking 3-4 lines out of say 100-line codes, that is nothing. But if 50%, more than 50% code is taken, that is plagiarism. Some matches will be there. And see, when we find plagiarism, we still see, or maybe it happened by chance. In the first sem, it was actually manually seen. Maybe this happened by chance because some template was given. But when you see whole block of code that was not given is copied just by changing the variable names, that is a clear case of plagiarism. Okay.
Sir?
Yes.
Sir, by directly seeing into the balance factor of the ABL trees, sir, can we say that whether the tree should be left rotated or right rotated?
Yes.
To balance the height.
Just for your checking conditions, right? So -2, -1 were nothing but the balance factors that I was checking.
Yes.
They are the balance factors. You can just make a condition on that. And actually, I'll just tell you, there is a code on GFG for this ABL, and that uses height. That does not store balance factor. That stores height at every node and computes balance factor by subtracting height of the right minus left. So you can do either way. You can either store a balance factor, or you can store height, balance factor, or store height. Okay, and compute balance factor from the height. So either is fine. So GFG has a code that uses stores height and computes balance factor from that. And you can see.
Okay, sir.
Sir, if
And
we
sir,
are
this ABL will come in the next week's assignment, not this one.
This will not come in this week's assignment. Okay. Okay.
Sir, if we store the balance factor, then we do not need to store the height.
Yeah, that's a good question. Actually, you don't have to, but yeah, this may depend how much your code will be, how much code you will use. Actually, you don't see. Once you understand the theory part, when you implement it using that, you know that if I do this right rotation, the height is maintained. You don't have to calculate that up. So you can do it either way. If you store balance factor just by doing calculation on what is the balance factor of this node of the parent, you can do everything. Okay, because you have seen all the cases in theory. So you just have to replicate that in the code. And if you use height, yes, you can compute balance factor and do things. So yeah, both ways should be fine. I don't think you have to store.
Thank you, sir.
Okay, then I think it was quite a long.
Sir, I emailed you regarding an issue with my code. Left 4.
Yeah, we will see that. We will see that. Sure. We will see.
Sir,
Yes.
so we asked you to give 2 weeks extension. I mean, 2 weeks gap between the theory and lab, right? Some people are telling to just extend the 3-hour deadline beyond 5. This
Yeah,
is
that's a
some
bit
people's
difficult. That's a bit
some people's
difficult.
request. Could you
I,
please
I,
consider
I
that?
understand. See, we did that already twice. We did that twice already. And yeah. Anyway, I'll discuss what can be done.
I mean, like
Yes,
if
sir.
it
Means
could be
the
increased
deadline
by an hour,
extension.
if at least it could be increased by an hour, like hour or two, it would be like very helpful
You don't
because
have
we have
anything
to.
from 5 to 6, I'm just asking.
You said that will be more helpful.
No,
You don't
sir.
have
After 5 o'clock, no classes, sir.
Sure, I'll discuss with the TAs on what can be done. Sure, yeah. So I have got a few suggestions. Let's see what all we can do. Okay, so sure, so thanks all.
Thank you, sir.
Thank you, sir.
Hello, sir.
Yes,
Thank you.
yes.
Sir, can you please stop the recording?
Oh yes, done. Stop recording.